Okay, so I promised a video to help review some of the topics on this final, and these are the general topics on the final. You have trigonometric equations, given ratio for trig functions and quadrant, find other trig functions, log equations, sketching angles and standard position, complex numbers, trigonometric identities, vectors. You have a lot of important stuff when it comes to trigonometry and pre-calculus. These topics are going to be used in calculus 1, even 2 and 3, dependent on what you're going to study in your future or what career you're choosing. You may or may not continue with math. Well, if you are, this stuff is importante. Okay, I do have where is it, these things that I have shared. I'll share them again when I share this video. You have what we call the trig cheat sheet, because it has all the identities and formulas that we need to know and you should memorize. When it comes to trigonometric functions, you definitely need to know the tangent and cotangent identities, reciprocal, Pythagorean, even, odd. Periodic, you should understand how they move. Double angle, half angle, you can get away with not knowing. You could technically derive the half angle formulas from the double angle formulas, sum and difference formulas. You can get away with not knowing some of these product to sum and sum to products. They pop up a little bit here and there dependent on what Calc 2 class you take. Again, like I said, that depends on what you're going to do in your future math. You definitely need to know your unit circle. I'm not really hindering reference sheets, but in future math courses, like I said, if you are going into future higher level math, you do want to know those. It will make your life easier. I'm going to do some of the problems here. I'll share some other videos on things that I can't necessarily cover, just based on time. I know you don't want to sit here and watch a long video, so I'm hoping to do this quickly just to give you an example of some of these things. A trigonometric equation is exactly what it sounds like, and it's an equation with a trigonometric function. And the thing about these is they vary, they change. They're not going to be exactly the same every time. So you're going to have to do a little manipulation depending on what it initially looks like. Well, this one, it looks quadratic in form. So that takes me back to algebra, right? So again, algebra, having a good foundation in algebra helps you with trigonometry. You can identify this as a quadratic pattern in trigonometric form because, I know my quadratic equations. Now, when we do trigonometric equations, sometimes we say that the angle is limited between 0 and 2 pi, which means that we're only looking for angles within one revolution. And sometimes we look for a general solution, but I don't think you're introduced too much into that in this course. Typically, you're looking at the particular angles within one revolution. Pay attention to whether we're inclusive of the ends or not. Sometimes you can have a bracket to include that value. This is called interval notation. So if I'm solving this, the one thing I want to start with is the fact that it's all in one trig function. So sometimes you can have a trigonometric equation and you have multiple trig functions, so you have to convert using your identities. If you can manipulate one trigonometric function into another and create one trig function from your for your equation, then that does help. Lucky for me, this is already all within, or all cosine. I don't have a sine and a cosine. If this was sine squared, for example, though, I could potentially use my Pythagorean identity to rewrite sine squared in terms of cosine squared. And then I could manipulate this in all as one trig function. That's an example of a situation that can happen where you might need a little manipulation before you go into the algebra. Now, I might, because everything is divisible by 2, simplify this quadratic and divide everything by 2, as long as whatever I do to one term, I'm doing to everything, and whatever I do to one side, I do to all. And so I'm allowed to mathematically do this. Now, if you need to rewrite this, as like a y squared to make it easier for you, then go ahead and do that. Or you could just factor it in trig form. This one factors, which is nice. 2 numbers that multiply to give me negative 12, but add to give me 1. That's a 4 and a 3. A plus and a minus, right? So if I were to multiply this out, I would get the same thing I have here. So that's how I know that I factored it correctly. Now I'm going to isolate, set each piece equal to 0. So cosine of x plus 4 is equal to 0, and cosine of x minus 3 equals 0. And I'm going to isolate my cosine function. Cosine of x is equal to, subtracting 4 from both sides, cosine of x plus is equal to 3. Now look at this. So this is an interesting example. If you recall, a regular cosine function, a regular cosine wave, is limited between -1 and +1. The minimum is -1, the maximum is +1, unless I have transformations or things like that. So technically, I can't have a cosine function equal to a value that is either less than 1, and I can't have a cosine function equal to a value that is greater than +1. So both of these situations give me no solution. I really can't find an x that satisfies those conditions. Now, I don't have a, if you want, using your calculator to find the angle here, you could use an inverse, right? To identify or isolate that angle. And on your calculator, if you're using a scientific calculator, if you do cosine of -4, cosine inverse, you get, wow, I have my phone calculator gave me a complex number. There's no real solution. That's the idea for this. There's no real solution, right? Because I can't have a cosine function equal to a negative. Now, if you guys plug this into your calculator, maybe you should probably get an error message, unless you have a certain setting on your calculator. Oh, see, I have it as complex, but yeah. So this one actually has no solution because of that situation. But let's just, for example purposes, let's just say that I have cosine x equal to something like I don't know, square root of 2/2. Maybe negative, just to make it a little harder. The idea would be to find values of x that satisfy this situation, and obviously you have to know the unit circle for that. Where is cosine negative? Cosine is like x, it's negative in quadrant 2 and 3. Well, where is cosine square root of 2/2? It's that special pi/4 reference angle. But if I'm in quadrant 2, it's 3 pi/4. If I'm in quadrant 3, it's 5 pi/4. So both 3 pi/4 and 5 pi/4 give me cosine of this negative square root of 2/2. So if I'm looking within one revolution, I would get two solutions for this particular situation. I would get 3 pi/4 and 5 pi/4. This is just a separate example from that one, just to show you, if you're continuing to solve and you actually have solutions, how are you doing that? So this is in radians. If I were in degrees, it would be 135 degrees or 225 degrees. So, technically, solving trigonometric equations really comes down to that, understanding, the unit circle. Typically, you guys won't see anything that's not really outside of that. Do we have situations that are? Yes, it's a little more complicated to find those angles, but not too bad, because if I do need to determine this x, this is where we use those inverse. And if you plug that into your calculator, you might get one solution, and you'd have to figure out the other based on reference angles and just what quadrant that cosine is negative. So basic kind of trigonometric equations, you can you'll see situations where it should work out nicely with the unit circle. I wanted to do one of these, so I'm going to rewrite this so it's a little cleaner. If sine of theta is equal to 2/3, and theta is an angle between pi/2 and 3 pi/2, which means this angle is in quadrant pi/2, and it should say in pi. Let me just hinder it within one quadrant. Between pi/2 and pi. Which means that it's within quadrant 2. Right? So they give you a trigonometric function equal to a ratio in the quadrant that angle is in. The quadrant is very important because it's going to tell you the sign, SIGN, of each of these trigonometric functions. So I want to find cosine I want to find tangent. I might as well do the rest, cosecant, secant, and cotangent. So I can find all of these other trigonometric functions just based on one. Now, if I'm in quadrant 2, let's just focus on the sine. Cosine is negative there. Sine is positive. Tangent is sine over cosine, so this is going to be negative, positive or negative. Cosecant is a reciprocal of sine, so it's going to follow the same sign, SIGN. Secant is the reciprocal of cosine, so it's going to use the same sign, SIGN, so negative also. And cotangent is a reciprocal of tangent, so if this is negative, this is negative. And sometimes I like to do that first so I don't forget after. Where does the rest come from? You can draw your right triangle in the correct quadrant. I don't necessarily always do that because I already considered the signs. It's just a preference. For me, I just need the triangle. Sine is opposite over hypotenuse. And so I could find the other side here. A squared plus b squared is c squared. 4 plus b squared is 9. B squared is 5. B is square root of 5. So that means that this side is square root of 5. Now you guys are watching a quick video. I'm kind of running through it quick. You can pause it. You can rewind it if you need to. You could do this on the side and then verify with me. Yes, I make errors, so you could check if I make an error. If you want to draw this in quadrant 2 to make yourself happy so you can see it in that quadrant, you could do that as well. But now I know cosine is adjacent over hypotenuse. Tangent is opposite over adjacent, which, sorry, my brain goes faster than my hand. Which means I have to rationalize this. 2 square root 5 over 5, right? Multiply the bottom and the top by the square root of 5 to rationalize. Cotangent is the reciprocal of tangent. Secant is the reciprocal of cosine, which again I have to rationalize. And then cosecant is the reciprocal of sine. I already took care of the signs, whether it's positive or negative, so I don't have to worry so much about that. And this, you might not be asked to find all the rest of the trigonometric functions, but you could be given one and asked for any of them. And that, it's not too bad, in terms of how to find them, as long as you have that right triangle and understand what quadrant it's in. Okay, I definitely want to do complex numbers. I think that this is something. Let me just see what I have here. Okay, I'll see what I have time for. But I definitely want to do complex numbers. This is something that is new to you. It's necessary when you go into future calculus courses. Maybe kind of difficult to understand, possibly. So I'm going to I have a complex number here. I want to graph it, write it in standard form, which technically it already is, and then convert it to polar form. So now converting into polar form is basically understanding trigonometric functions as well. And polar form is a very cool form. When we have, and I'm going to write this on the side, you guys are so used to this. You see rectangular coordinate systems, and you've seen this so many times. And I think that's why when we get to pre-calculus, sometimes it's like, what just happened? Because you go from this rectangular coordinate system that you're so used to, x-axis, y-axis, to a potential complex system where you have a real axis and an imaginary axis, to a polar coordinate system, which is crazy because polar coordinate system runs, in terms of distance away from the pole and an angle to determine the location. Basically, identifying or graphing an angle from standard form. So we move out from the pole to determine, so that's kind of the magnitude, how far away from that pole we are, and then where on this circle we are located. That's how we graph things in a polar coordinate system. Polar, complex, rectangular. So when you get to pre-calculus or trigonometry, you learn these other systems and you're like, I feel like you're so used to rectangular that this becomes like hard to like grasp. I would I think if I have videos regarding polar systems, there's some really cool graphs that can happen on a polar system that can't really happen easily on a rectangular. That's why the polar coordinate system is so cool. You can get like cool looking graphs on a polar system. Like you can get what we call rose curves. You can get like swirlies. These kind of things can't happen very easily, like I said, on a rectangular coordinate system. So sometimes converting to polar form, it's easier to graph. All right, well, anyway, I want to take this complex number in order to basically graph this. Not x, see, look at that. I have to graph it on a complex system. Can't graph it on a real because it's not real. I have a real and an imaginary axis. And, you know, this is not extremely different from x and y because when we talk about a complex number in standard form, a plus bi, the a is kind of the real part and the b is the imaginary part. So the a is kind of the horizontal movement and the b is the vertical movement. So if I were to graph this complex number on a complex system, I'm moving -3 in the real axis and +3 on the imaginary. So this becomes a dot here, located in like this second quadrant on a complex system. Now, I want to be able to identify this location if I were to put it on a polar system. So I need to rewrite this -3 + 3i in polar form. And when I say polar form, then that means I need what we call like a magnitude and a direction. You know, kind of like how far away from the pole am I? And then what angle there is kind of corresponding to that location. So what helps with that is, you know, again, I mean, it's not, you know, craziness. A right triangle can be created where the base is 3 units and the height is 3 units, and the angle here is the reference angle that will help us determine the actual angle from standard form. So I can now identify the distance from here to here. Oops. Right, this is what I want to know. How far away from the pole, and then I need to know this reference angle so I can get the full angle to put my thing in polar form. All right, so technically I'm finding the hypotenuse of a right triangle. So, you know, I'm taking the square root of this squared plus this squared. Really, it's the same thing as finding the hypotenuse. A squared plus b squared is c squared. We just don't have the squared here. We square root this whole thing. So what do I have? 9 rad 2, right? I should say not 9. 3 rad 2. Let's see. Square root of 18, 3 rad 2. How do I determine this angle? Well, we usually use tangent, opposite over adjacent. We say the angle, tangent of this angle is opposite over adjacent, or the angle is equal to tan inverse of opposite over adjacent. This is just for the reference angle, okay? And where is tangent equal to 1? That reference angle is pi over 4. This is just the reference angle. Now, you know, you could put it in degrees or radians. I think you should understand both. But this angle that I'm looking at specifically now has to be the angle from here to here. Now, if the reference is 45 degrees or pi over 4, and I'm looking at the angle in quadrant 2, 135 degrees or 3 pi over 4. Depending on if we're referencing it, if we're writing it in terms of radians or degrees, because both are fair game. So then we have polar form. And this is something that I would probably say to add. If you want, you can add it to your reference sheet. It's not on here because it's not really part of the trig cheat stuff, but you can write polar form yourself. So this complex number represented in polar form is okay, so where's my r? 3 pi over 2. 3 times square root of 2 sine of, I'll put it in radian, pi over 4 plus 3 square root of 2 cosine pi over 4i, 3 pi over 4i. If I were to multiply this out, cosine of 3 pi over 4 is negative square root of 2 over 2. Then watch what happens. I get 3 times 2 over 2, 3. I get negative 3. So when I simplify this, oh, I switched it. I'm sorry, guys. I don't know why I did that. It happens. Cosine. 3 times square root of 2. I don't know why I switched that. Cosine of 3 pi over 4 plus I sine. Oh, sorry. Uh, 3 times square root of 2. Careful. 3i. I'll put the I there. Sine of 3 pi over 4. This is polar form because it's represented in terms of, like I said, the distance from the center and then the angle to allow us to identify this location. Typically, polar form includes trigonometry value like cosine and sine. Don't forget the I for that second part because that's the imaginary part, but you can determine if this is correct because if you were to do cosine of 3 pi over 4, which is what I was just showing you, negative square root of 2 over 2, and if you were to multiply that by 3 rad 2, same thing with this, you should simplify into negative 3 plus 3i. So going from polar form to standard form is a little bit easier because all you're doing is multiplying it out. Find cosine of the angle, multiply it by the value in front, find sine of the angle, multiply it by the value in the front, and it will give you your complex number in standard form. Converting from standard form, which is this, into polar form is a little bit more complicated because you have to find out, like I said, that distance and then the angle corresponding to that location or the quadrant that the angle's in. And we represent it. Why is this thing tripping on me? We represent it in this form. So we kind of look at it as a magnitude and like an angle. I work with reference angles a lot, and then I determine quadrant. I mean, everybody's different how they do this stuff, but if you have the unit circle in front of you, it makes it a little bit easier. So standard form of a complex number is this. Graphing, you have a real axis and imaginary axis. It's very similar to rectangular where you have a horizontal and a vertical movement, but converting it into polar form, you got to find a value that represents the distance from the pole, to that point, and then an angle corresponding to the location of the point to give you that quadrant. So that's where it's almost, it's the same thing as a squared plus b squared is c squared to get the hypotenuse, and then we use tangent to represent or find the angle because we typically have opposite over adjacent. I use reference angles. You can go straight to the angle because of the unit circle that you can have your reference sheet. So these are complex numbers. Trigonometric identities. This, I'm going to share a video that deals with trig identities where I do some examples because there are a lot of different variations of trigonometric identities, verifying trig identities. And it involves, algebra. You should know factoring. You should know how to deal with complex fractions, right? You should know how to deal with rational expressions, where basically fractions. I'm sorry, I know nobody likes fractions. Adding and subtracting fractions, multiplying and dividing fractions. And a lot of times with trigonometric identities, if you can't identify a particular algebraic move, if you can rewrite it in terms of sine and cosine first, sometimes that helps simplify. And there are different ways. Sometimes there's multiple methods to get to that conclusion. So with trigonometric identities, sometimes it's, you know, it takes practice. You just have to play with a bunch of them. And that's what it is. It's like a puzzle you have to figure out. So I will share a video that I have where I do some examples of trig identities to kind of give you a review of that. What do I have? Sum and difference. Okay. Sum and difference formulas. Which I hope that you guys memorize, but if not, it should be on here, right here, sum and difference formulas. And this is where we can rewrite sine of a function, cosine of a function, whatever, in terms of a different angle. It allows us to manipulate this angle to get, here's a lot of the indicators, exact value of an expression. So, you know, if I write sine of pi over 12 is not a special angle. So I can't find an exact value of this. I could plug it into my calculator and I could find a value for this, you know, and you know, an irrational number probably. But, you know, the exact value of this, I can't determine because pi over 12 is not one of my unit circle angles. So the goal behind this is to recreate or rewrite the angle here to find the exact value in terms of your special angles on the unit circle. A pi over 6, pi over 4, pi over 3 type of situation, or any of these. Now, pi over 12 would be, we could represent it as 4 pi over 12 minus 3 pi over 12. Right? I'm not changing the angle, I'm rewriting it. So 4 pi over 12 can be represented as pi over 3, which is good because that's a unit circle angle, and 3 pi over 12 can be represented as pi over 4. So I'm able to rewrite pi over 12 as a difference, in this case, of two unit circle angles. Looking at the sum and difference formula for sine then, okay, I get sine, cosine, cosine, sine. So this is kind of how I like to memorize it. Sine of some angle, cosine, cosine, sine. I like to set it up that way. I memorize these where the sum and difference formula for sine is sine, cosine, cosine, sine. For cosine is cosine, cosine, sine, sine. And then tangent of the first, tangent of the second, and then 1 times the product, or plus or minus the product. And you just have to memorize whether you're following the sign or doing the opposite of the sign. This is just a way to memorize these. If you have it in front of you, you obviously don't have to memorize it, but again, that's just a little trick to memorize them. But if I have a difference here for sine, then I have a difference overall here. Ugh, why does that happen? And then it's really just the first angle, the second angle, and the first angle, and the second angle. Okay? So if you're looking at it here, sine of an angle plus another angle is equal to sine of the first angle times cosine of the second, right? Plus or minus cosine of the first, sine of the second. So I set it up following the sum and difference formula for sine. And now I'm just simplifying. Where are you at? Okay. My unit circle. That's what I was looking for. Sine of pi over 3. I go to pi over 3. Sine is the y coordinate. Square root of 3 over 2. Times cosine of pi over 4. Go to pi over 4. Cosine is the x coordinate. Square root of 2 over 2. These are these are things that we should memorize, right? I'm showing you with the unit circle in front of me, but it is something that I hope that you know by heart. Pi over 3 is here. Cosine is the x-coordinate, 1/2. Right? Pi over 4 is here. Sine is the y-coordinate, square root of 2 over 2. And then we just simplify. Square root of 3 times square root of 2 is square root of 6. 2 times 2 is 4. And then I have common denominator. I can rewrite this as square root of 6 minus square root of 2 all over 4. And this is the exact representation of that solution. So if I want, I shouldn't really get these wrong, because if you plug into your calculator sine of pi over 12 and you get a number, just make sure that your calculator's mode is in radians if you're going to use an angle in radians. And I plug this into my calculator properly, square root of 6 minus square root of 2. I would, if I were you, put parentheses around the numerator. If you're plugging it all in, be careful with order of operations. Your values should match. Because you're finding the answer to this. What is this number? Well, I could plug it into my calculator and get a decimal, but since we're asked for the exact value, that's why I'm going through all this. So, angle of elevation. This is an important topic too. That's why I wanted to cover it as well. So, anytime we're doing angle of elevation, so elevation is elevated from the horizontal. So if I'm talking about an angle of elevation from where this person is located, I'm talking about the angle elevated from that horizontal. So this theta would be the angle of elevation. Now, sometimes you get the height of a building. I don't know, let's call it 100 feet. We'll just make up numbers. The height of a building. Sometimes you get the distance that the person is from the building. I don't know, let's call it, I'm making whatever, 50. I'm just making up numbers. If somebody is 50 feet from the base of a building and the building is 100 feet tall, find the angle of elevation. Or sometimes they give you the angle of elevation and they give you the distance the person is from the base of the building. Find the height of the building. At the end of the day, it's all a right triangle. And no matter what, as long as I know two things, I could find anything else. Okay, I just need to know two things about this triangle and I could figure out any other part of this triangle. I could figure out the hypotenuse. I could figure out all the angles using my trigonometric functions. So I can know this angle and this base and find the rest, or know this angle and this and find the rest, or whatever. That's the idea is which trigonometric function would make it the fastest. So if this is the angle that I want to find, and I know the opposite value of that and the adjacent value of that, then it would make sense to use tangent, right? So it just depends on, here we go again. It just depends on, what I have for that triangle. SOHCAHTOA, by the way. Here we go again. SOHCA, I really hope you guys know this. Sine is opposite over hypotenuse. Cosine adjacent over hypotenuse. Tangent opposite over adjacent. I hope you know SOHCAHTOA because that's right triangle trigonometry. If you know sine and cosine, you could potentially figure out the rest because tangent is sine over cosine. But knowing the three basic functions, you could take it from there into anything else. So I'm using tangent because of what I know and what I want. I want this angle and I know opposite and I know adjacent. So I have tangent of theta is equal to 2. So how do I find this angle? And whenever I want to pull the angle from being attached to the trig function, this is where those inverse trigonometric functions come into play. So if tangent of theta is equal to 2, then theta is equal to tan inverse of 2. And I do this because this is what I'm plugging into my calculator to be able to get that angle. If it's not a right triangle, if it's not a unit circle type of situation, make sure that your calculator is in the correct mode. With something like this, we typically use degrees. You'd have to change the mode of your calculator by pressing mode, put it in degrees when you need it in degrees, put it in radians when you need it in radians. I want this angle in degrees, so my mode's going to be in degrees. And I'm going to do tan inverse of 2. And my angle, depending on how I went around, I'm just going to go 63.4. We'll go to the 10th. So this angle of elevation here is approximately 63.4 degrees. But again, like I said, this could change. Like, I could know the angle and want to find the height of the building, or I can know the angle and want to determine how far the person is from the building, or it could be a kite, or so this situation can change. It's just to create that triangle, write down what you know, and then use what you can to get what you don't know. Use what you can, right triangle trigonometry. So I think I'm gonna have to give videos on the rest of this, zero and their multiplicities, because I'm running out of time. I don't want you guys, I know you don't want to watch long videos, so I'll share some other videos on some of these things. I might do this one, variation. I always get questions on variation, so I might do this one and then share videos on the rest. Direct variation. So if y varies directly with x, we say y is equal to kx. That means as x increases, y increases. As x decreases, y decreases. K is a constant of variation. There's always a constant of variation there. When we talk about how y varying directly with x, we're just saying y is equal to something times x. If it's inverse variation, we say k over x. We call it inverse variation because as x increases, y decreases. As x decreases, y increases. So, but if I have joint variation where y is varying directly with x and inversely with w, then I'm saying, well, y is equal to k times x over w. I don't need two k's. There's only one constant of variation per equation. So typically when they do variation problems, they say, well, hey, y is varying, or whatever, some variable is varying this way with another variable. Could be joint, could be direct, could be inversely by itself. And then they give you numbers. Well, when this is equal to this, this is equal to this, this is equal to that. If that's true, then find this value when these are the idea is this is given to you to find k. What is the constant of variation? So I plug it in, I get y is 3. I don't know k, x is 5, and w is 6. I can find k. K is equal to 6 times 3 is 18 over 5. Ugly, but that's okay. So that means this general formula, y is equal to 18 over 5, x and w. This is the constant of variation. It's directly, it varies directly with x, inversely with w. But now, no matter what values you give me for x and w, I can find y. When x is 3 and w is 4, find y. Plug it in, we can find y. So I wanted a quick example of that because you see variation everywhere, and I know sometimes variation could be, I guess, complicated, but it's not that bad. So I wanted to do at least a couple of examples for some of these. And then I'm going to share some videos separately that are like quick videos on some of the other topics. And I hope if you have any questions, reach out. I hope that helps with your final review. But again, like I said, if you have questions, please reach out to me if you're stuck or on any particular topic. Okay? So thank you for watching. I'm sorry, I know it's probably a half-hour video. So I'm going to cut it there, and I'm going to share this now.